afternoon, everyone, and welcome to the new PDE seminar. And today we have Javier Monreal, who's going to talking about a variational approach for the singular perturbation domain with open system. Go ahead.
Thank you, Jessica. Thank you for the introduction. Thank you for your assistance. It's a very big pleasure to be here. Oh, what it changed? To be here. I always see the talks here, very high level talks, so I feel I'm honored to be part of this seminar today. Okay, I'm going to talk to you today about what has been the work that I have been doing with Professor Mike Kowalczyk during this year. We're already on September, very, very fast. So, okay. This is the order I'm going to follow during the presentation. First, in the introduction, I'm going to give the context where the problem that I study arises. More than one. Why is it interesting to study the problem with a singular perturbation approach? That means that we are going to have a parameter, a real parameter, that we are interested in knowing what happened when this parameter is zero, when it's not zero, and what happened in between when we have this limit and the connection between the solutions. After that, I'm going to write the setting of the system with a mathematical language, the set of functions that we are going to work with, the energy functional and the potentials associated. Then in 3, what are the existing results that we have with this configuration? Then study the same for the singular limit problem with the singular parameter equal to 0. And then study what happened with the connection between these two problems. That is the principal question for this. And what happened, okay, the behavior of the solution when the perturbation parameter goes to 0 and if they are connected. Finally, under some change of variables, change of, and another scaling, it is possible to see that the singularity that it is generated here can be modeled in the limit using a Painlevé equation. So we are going to see a little bit of that at the end too. So let's go with the introduction and the context of this. First is the pattern generating systems. Okay, in the study of diffusion equations, it is not unusual to find solutions like this. Okay, we can see some spatial structure in the solutions. And we can see stripes, we can see corners, can be formed squares, and many other different forms here. So we are particularly interested in the structure that we call a domain wall. A domain wall is a transition between stripes, okay? If we consider rotationally invariant systems, the most basic pattern that we can observe are stripes. So if we have these rotational invariant systems, different stripes with different direction can coexist. And given that we can generate stripes with different directions, we should have some transitions in some part of the space. This part where this transition occurs is called a domain wall. We can see here, for example, we have squares generated in the transition of the stripes. We can see here in a perpendicular transition, and here this is the more general case. Given that we are working with rotational invariant systems, there is not a coordinate system previously. So what we can do is consider, for example, in the right-hand side, the figure, consider this coordinate x and y, and try to find an equation that tells us how is this behavior. What we usually do is use something called amplitude equation, which is to assume that these stripes are oscillations of some amplitude function. Okay, what we want to see is what we have this oscillating function and some amplitude that is the envelope, and it goes from 1 to 0 because it disappears. This set of stripes is going to fade, and the other one is going to appear. So what we want now to model this transition and the domain wall is to find an equation for the amplitude. If we do this, this is the equation that we get. This is called Gisborne-Landau system of equations. And given that we are now interested in the structure of this domain, well, we are going to consider stationary solutions. So time derivatives are going to be 0. Also, we want to know about when no squares are generated. This is going to be when mu is greater than 1. And okay, we seek for non-negative solutions with heteroclinic boundary at infinity. Okay, so for from one stable point to the other. Okay, so we have Gisborne-Landau and pattern generating systems, and at the same time, the other one, we have the connection with system. This linear version of the Schrödinger equation, and in the case of modeling binary mixtures of Bose-Einstein condensates, this system appears. If we consider the standing wave solutions, which are these, with these constants on this equation, we are going to get again the previous equation, okay? Like this Gisborne-Landau equation. And if we set the conditions at infinity, we get back to our previous problem. And if we consider the stationary version, we get system. So it happens that in the context of Bose-Einstein condensate, it is usual to use something called a Thomas-Fermi approximation. That is to assume this constant d2 to be 0. This is neglecting the kinetic energy of the Bose-Einstein condensate, which is considered small in comparison to the external forces of the potential and the self-interaction of the Bose-Einstein condensate. In the case of the pattern generating system, this d2 is arbitrarily small in the case of the perpendicular transition of the patterns. So it is in both of the problems, it is usual and it is interesting to see or to neglect this. It is an interesting problem to study, an unusual problem we study. So the question is, if we can like naturally and continuously neglect this term with some perturbation parameter and see if there is a connection between the solutions, because the solutions of the system are well known and the solutions when we consider the Thomas-Fermi approximation are also well known. So what is the situation of the problem? As you said, this problem, the stationary version, is variational. We have many tools. Wave solution for the gross. There are results on the mass approximation solutions are with energy is neglected. So the natural question is to ask if the Thomas-Fermi limit solution and the general solution, considering this kinetic energy, are connected. Okay. Also, there are some works from Clerk and Marshall, classic in 2017, and when a similar problem, a little bit different, and they use change of scaling and look for a natural scaling for a singular perturbation problem and see that the singularity, this singular perturbation problem in the limit can be modeled using a Painlevé equation. So it is also the question that in this case, if in this case we can do something similar. So that is the context. Let's see now the system. How are we going to work with it? So this is the system that we are interested in. Okay, now we are now D2, D1. We are interested in here. Mu is greater than 1. So the energy associated this potential is like a W. You have these in real variables that have two minimums, 0, 1, and 1, 0. It is coercive, and we are going to work with this set of functions and with the function. I'm going to just, yes, this is like 3 slides, something like that. I'm just going there. But I can show you that. It's coming, it's coming. The potential. How it should be this? I haven't thought about this like in 2D, but it's like, I think, or like a radial version of something like this. Like or if you consider u, like this, the value is going to be 1, 0, 0, 1, something like that. Yes? It's kind of weird. Okay. So I'm going to see the solution explicitly. We know the solution explicitly when epsilon is 0. So for the case of epsilon first, the general existence results are this. Okay, we know that there exists a minimizer of the energy. We can prove it in the previous set. And also we know that all solutions of the problem that fulfills the conditions at infinity are necessarily monotonic functions taking values between 0 and 1. This is very useful because we want some convergence result. So given that we have these uniform estimates for the values, we will be able to get very much. If we see the equation, for example, I can take all to the other side and get an uniform estimate for the second derivative of u. Now, the thing is that I cannot do the same with v because we have this singular perturbation parameter. So if I want to divide by epsilon, I cannot get a uniform estimate for all the family of solutions. So we are going to work with that soon with some other tools. So, but this is a really good result, and we are going to use it. And now the singular perturbation problem. These are the solutions that we have when we assume epsilon to be 0. We just solve the equation. One is a second order differential equation when boundaries are infinity. We can solve it. And the other one is comes from the algebraic equation that comes with the epsilon equals 0 case, okay, equation. So what can we say about these solutions? The first one is Lipschitz functions. We can prove it. And the second one is a Helder function with exponent 1/2. I'm going to write how is B0 because it's going to be useful for us. Like B0 looks like this. It's very similar to the square root. And then it's 0. So this is C. Well, okay, so we have this. And this is B0. Is big enough? Yes. C, yes. Yes, it comes because of the autonomous system. So you can have displacement. X1 and these are known functions. But yes, C is free, you can make displacement. Okay, so that's what we have. And okay, these solutions are well known, but we haven't found that are like formally well characterized the uniqueness. So here we write it down. Okay, the equation when epsilon is 0 admits a solution u0 v0, where u0 is Lipschitz, v0 is Holder continuous with this exponent. Moreover, these are the unique solutions in this set that fulfills the conditions at infinity and that minimize these functionals up to a constant displacement. So now what we are going to do is to take the solutions that we have with epsilon and show that they converge to a function that minimizes this functional and fulfills the condition at infinity, and so must be a displacement of u0 v0. So we will have the convergence that connect both of the solutions. Okay. Now what happens in between? Okay? When the perturbation parameter goes to 0. Okay. We already have some estimate for u, but we don't have for v. So how are we going to get this? We are going to use this. This is like the big result. That is this energy estimate. Okay, this chain of inequalities, what tells us is the following. The first one is maybe very natural because it tells us that the energy associated to the Thomas-Fermi approximation takes lower values than the problem considering all the terms, even if we minimize. That is very natural. But the thing is that the difference between them is not that big, is proportional to epsilon squared. So that is very good because that will allow us to get an estimate for this, because the main difference between these two terms is the one associated to the energy of v, or the derivative of v. Okay, this part multiplied by epsilon squared. So given that the main difference of this is we have an estimate on epsilon squared, we're going to get a uniform estimate for the family on this derivative. Okay, So that will be enough because we have L infinity estimate for V, and now this will give us L2 log or H1 log, and we can go with usual compactness arguments then. So let's see the proof of this estimate. The first one is very natural. It's just, okay, first we see that the Thomas-Fermi approximation energy take lower values. And given that U0, V0 minimizes E with the tilde, then we have this first, the first one. Now for the second one, we want to use the minimizing property of U epsilon V epsilon. But the problem is that this function doesn't necessarily lie in H1 log because it has this singularity point. So we have to do something with that because we cannot just use this estimate and put V0 here. So what we do is take a modification for V0. We consider a small interval where we're going to make a modification here, here, and take a linear interpolation of the values. Okay, that is what we are going to do. And these functions, this function, we can we call it. Oh, it's red. I don't know if you can see red. It looks good. Yes. Okay. No, no, don't worry. No problem. No, but it's a linear interpolation in this interval. Okay. And what is theta means? And so now we can use the estimate the minimization with this function V0 with this bar. And so we divide these terms, the associated with the Thomas-Fermi approximation, and the term that we are neglecting, we take it to this side. And what we are going to do is to prove that this term can be bounded by big O epsilon squared, and this energy is not that far from the energy associated to U0 V0. Those are the steps. So the first one, okay, we can prove that outside the interval, this interval when the singularity lies is proportional to epsilon squared. And now we want to see what happens inside the interval, okay, with the energy can go high. And so to do that, what we do is to make some expansion analysis on V0, which we know, okay, we know explicitly, so we can do it and see that as epsilon goes to 0 from the left-hand side, in this case, it looks like the square root. Yeah, that makes sense because it's a composition of the square root. We just said that it's a 1/2 Helder function just at the square root. So we can prove this with expansion analysis. So we know that this height, for example, is O epsilon alpha over 2. And with that, we can, we know how is this, the derivative is just the pendiente, the derivative here of the linear function. We can have it. And we just have an easy estimate to get with that because we know explicitly that this is an affine function in this interval. We get the estimate. So we were able to get that part. Okay, this we have this then. Okay, this term is have this bound of epsilon squared. Now we have to see the other one. But the other one, we can note that if we have this difference between the bar and with no bar, that okay, U0 is the same, and all the terms here are proportional to V0, not the derivative of V0, nothing like that. No, just V0. So given that we know that V0 and V0 bar have values between 0 and 1, all this is going to be, and all the terms coincide except for this set, this interval. The difference is going to be proportional to the length of the interval. So what we do is take alpha equal 2, and we're going to get this, that this difference of energy is going to be proportional to epsilon squared. So that's, now we have the energy estimates that we want. So that allows us now to show the result that we want, which is the connection between the solutions. Okay, so we have that for all sequence of epsilon going to 0. There exists a subsequence that converges, okay, point-wise in the whole real line, C1 alpha log and C0 alpha log for U0 and U epsilon and B epsilon respectively. And the limit functions are the solution of this equation, which is the Thomas-Fermi limit approximation equation, and satisfies the boundaries at infinity and minimize the functional. And so we have all these conditions. So also we are a displacement on U0. Now see how is the proof? We have all the ingredients. Can we have these uniform estimates for the values of U epsilon, B epsilon? We have so the uniform estimate for the second derivative of U. We just have proved these energy estimates that allow us to show the uniform estimate for the family of the derivative of B. So we have uniform estimate on H2 log and H1 log. So we Grelic Kondrakov theorem and diagonal argument, we can get the convergence that we want, and it is on the statement. Now, what we want is to show that indeed these limit functions are the minimizer, have the boundaries at infinity, and okay, so it's going to be a displacement. We want to show that, but we know that the energy functional have just positive terms, so we can use photo lemma and see that the energy of the limit is lower or equal than the limit of the energy. And using now the energy estimate that we proved before, we can take this here, we get this estimate, replace it, and taking epsilon to 0, we show that necessarily the energy, okay, this Thomas-Fermi energy, we call it, okay, approximation energy, has to be equal to the minimizer. Now, using other techniques, it is possible to prove that the limits at infinity coincide with the ones that we want. And we conclude with the theorem about the uniqueness that must these limit functions must be displacement on U0, V0. Okay, so we have this first part fully covered. Now we ask, what happened with this singularity? Is a natural scaling to capture how this singularity is? The Painlevé equations are equations that born in this context. So let's see if we can find okay, now focus because we have our first result. We have the connection on the solutions. Now we'll focus only on B, which is the one that has this singularity. Is there a characterization of singularity? Can we see something like that? And so we take the equation for B and look for a natural scaling to take this epsilon out of the equation in some way. So we consider this change of variables. Now, if we do it, we work it, we're going to get this equation here, okay, for what we call phi sub epsilon. And in the right-hand side, there is this function h. Okay, now, okay, we do this change of variables, and this is the result associated to this, which is looks very similar, but we don't have the same things as before. I'm going to tell you, okay, we have that for all sequence of epsilon, there exists a subsequence that converges to a limit function, point-wise in the whole real line, C0 alpha log, alpha between 0 and 1/2. And this limit function is a solution of this problem, which is a Painlevé equation. Now, to prove this, what we need is these two propositions. One of them is to show that this phi sub epsilon is a bounded family in L infinity. And okay, this is another technical one, which says that the right-hand side can be divided by epsilon over to the power of 2/3 and it's still going to 0, okay, in any interval. Yes, yeah, I was going to. No, yes, of course. The thing is that why is this different? Previously, we had at the beginning, we had this uniform estimate on the values of u and b. We're taking values between 0 and 1. Now, phi, given that this change of variables is divided by epsilon to the power of 1/3, so if we consider epsilon going smaller and smaller, we can lose control maybe of the values. It makes sense. But the thing is that, okay, we cannot have now necessarily a uniform estimate in the whole real line, but we can have it locally. So it's L infinity log the estimate that we have here. And we're going to okay, so I'm going to see first how is this proof, and then the proof of the theorem. So we consider the equation for V. We multiply by a compactly supported bounded function like this and integrate. If we use all we had before, because we have it, we can use integration by parts and Cauchy-Schwarz to see that this term that has the second derivative of V can be bounded by big O of epsilon to the power of 5/3. All the other terms appear naturally if we just order the terms. Okay, we obtain this, and if we smartly, okay, multiply the left-hand side and divide by epsilon, we're going to get this, and under this, okay, change of variables, we are going to get that the left-hand side actually is phi that we want to get an estimate for. Okay, let's go a little bit slow here. Okay, so, okay. So at the right-hand side, we have this big O epsilon. Side we have this epsilon 2. So it's able to show that this part here is also big O of epsilon 5/3. We're going to get a uniform estimate. Well, depends on phi. This phi is a support function, but we can use a bump function to, okay. So we are going to get a uniform estimate in this case for L3, okay, for L3 for this. So all we want to do now is to show that this part with the asterisk, this part have this bound. So what we do is, okay, without losing generality, because we have this, we can move this, you can take this singular point C to be 0, okay, without losing generality, and have a subtraction here for this term. We do it, we multiply by these terms to get use of the 1/2 Helder inequality that we have, and we can have an estimate for this term. Okay, so this term is going to be bounded just as we want. So we get it. We get the estimate that we want, and finally we conclude that we have this estimate. This estimate is depending on phi, but we can use some smart function, bump function, to have a local estimate. Okay. Okay. We have a uniform estimate in L3. Also, using the uniform estimate that we have for V, we integrate this. Okay, this is just a computation, but we get the same estimate for phi. We also have that the derivative of phi is uniformly bounded. So we have L3 log, so L2 log, and so we have a H1 log, and so L infinity log. Okay, so we have the L infinity. Now we can just, as before, prove the theorem with the convergence, and the techniques are very similar. So we have this equation phi after we do this change of variables. Okay, we have this L infinity log and this, so uniform estimate on H1, compactness, diagonal argument, and we get in the sense that we say in the statement of the theorem. Now, if we multiply the equation both sides for compactly supported function in the where we are working, okay, inside here, we get this. The left-hand side, we get a weaker version, okay, of the equation, and by dominating the convergence theorem, the left-hand side converges, and the I did the proof, short the proof. We know that the h divided by this term goes to the goes, and we conclude that this limit, the limit function, is necessarily a weak function of the equation. This is the Painlevé. And so, okay, final observation and comments. Okay, we were able not only to get solution and the connection of the problems, but also have a very good characterization of how is this singularity can be modeling the limit using this Painlevé II equation in this case, because there is a family of Painlevé equations. This particular is called Painlevé II equation. So this is what we have done here. So this is the references, the figures, all the things that I cite. Thank you.
Thank you so much for very nice presentation. And now we can have a question. May I ask you a question?
Yes, when you prove the existence of this part, like on the original problem, you have to not necessarily like fix, but the solutions that you get are like centered in some way. Like these are not like free solution necessarily. They have like some restriction between them. Yes, yes. This one?
Yes, right.
Like if the domain wall is like a curve, for example. Mm, I think I think the thing I know about this is like any of these defects have their different approach. So if the domain wall, as long as I know, has to be like a straight line. If maybe you can do a zoom and get a straight line, but if it's not at any, maybe it will belong to another family of topological defects. I think would be something like that.
Come back to the part of the definition.
Yes.
Or
Here.
yes. If you change the differential operator, you have two derivatives here. If you change for another differential operator, do you believe that you can use this technique to improve the result?
Let me think.
Like a homogeneous derivative or something like this?
Like a what? How?
Homogeneous derivative.
Okay. All in the part of the differential operator, all we used was the estimate that we knew before for B. So if you have some estimate for that part, you can. And you, of course, you have to have, in this particular case, this term can be bounded using this Helder. So it will depend maybe on the structure and what you have. But for example, if you only change the differential operator, if you can get an estimate, it is possible. But the hard thing here, because we tried with a four order also, or four order derivative. But the thing that was hard was to find a good power for this. Like you have to be able to control in some way that the powers will be the same in some way, okay? So if you have an estimate, a good estimate, you should be able to repeat this, I think. Yes, 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 yes. The quality is this has to be a relation between the quality of the estimate that you have for the differential operator and what you are trying to get here, like thing like. Yes.
The Painlevé equation is typical for that, but the Painlevé equation, but explicit or well known. So what is the use for the behavior of dx equal to 0?
Ooh, no, that is a hard question. No, unfortunately, I'm not big expert on this Painlevé transcendence. I have tried to read about it, but no, the thing I know that they use it, they some way characterize these poles that can move. So I think maybe characterize that we have indeed like this we are free to move this like under displacement. So that makes sense when I saw that Painlevé equations are used for that, but I don't know much more. There are okay, there are many of them. So maybe Painlevé II equation particularly have some properties that you can get. Like maybe all different of them have things, but hard to know. Hard to answer this. Mm.
And then to compute analytically
Mhm.
properties that the energy that we have better, you can have computations. There are people that have done for years
Mm.
with Painlevé. So you can do something for the energy when you go back to the next slide uniformly.
You see that you can maybe reconstruct some information. Yes, yes, of course, yes. The limit, yeah, what happened? It's possible, yeah. Because yes, yes. So yes, thank you for the question. Everything. Pero-
Semana ¿cierto? Y la siguiente no tendremos seminario en ustedes, porque tenemos la jornada de 24 diferentes 24. También, por favor. Y la siguiente sesión será 30 de septiembre.
Ay, por Dios. ¿Qué? Ay, qué. Sí. Sí, al principio un poco, después ya lo mismo. Es que como que uno ya después como que se mete